Okay. So good afternoon. It's a pleasure to have with us Professor Thomas Conrad uh, from the School of Chemistry and Physics, University of KwaZulu-Natal in Durban. So Thomas has been a regular visitor in math science, maybe about last 10 years or so. I mean, due to this pandemic, he couldn't visit, and some of us also visited him a couple of times, particularly myself. So Thomas is a well-known figure in quantum information, quantum computation, and particularly in the optical implementation of quantum information processing task. So let me, people who don't know him, let me try to briefly introduce Thomas. So Thomas did his diploma degree in physics from this Eberhard Karls University, Tübingen, Germany, and his diploma of physics was on this application of a new theory for highly eccentric satellite orbits at the example of Mars 96 mission. Then he did his master's in quantum fields and fundamental forces at Imperial College London, and the master thesis was non-perturbative methods in quantum field theory under the supervision of Professor H.F. Jones. So thereafter, Thomas did his PhD at the University of Constance, Professor J. Aldrich. Maybe I'm not spelling it correctly, pronouncing it correctly. So his PhD work was basically on quantum measurement. In particular, it was on the theory and applications of weak and unsharp measurement in quantum mechanics. So okay. And then, he had lots of affiliations, etc. So he was affiliated at the Institute for Theoretical Astrophysics at the University of Tübingen. Thereafter, he basically participated in the Mars 96 mission on behalf of German Aerospace Center. And he also, participated in the project on quantum field theory on quantized space-time at the University for Vergata in Rome, Italy, under the supervision of Professor J.E. Roberts. So he was also a scientific collaborator at the Optics Zentrum Concepts, and a postdoctoral fellow thereafter at the University of Constance. So he supervised this project CAP07 at the Center for Applied Photonics together with Professor J. Ordjetz, his PhD guide. And then he was a guest researcher at the Institute for Quantum Optics and Quantum Information, Austrian Academy of Science, in the group of Professor Hans Briegel, Innsbruck, Austria. So since 2006, he has been a faculty member in the University of KwaZulu-Natal in Durban. So currently he is a full professor there. So I know that Thomas is involved in several activities related to these particularly these quantum information computation optics in South Africa. So he is a member. He was a member of the Council of South African Institute for Physics and chair of Marketing and Outreach Committee of SAIP. He was the editor of SAIP online journal Physics Comment. He was a guest researcher at the Wigner Institute, Wigner Research Center for Physics at Budapest, Hungary. Since 2017, he has been a member of the Senate for University of KwaZulu-Natal. And since 2018, he has been a representative of the professional body of SAIP, this KwaZulu-Natal Provincial Skill Development Forum. Okay, so he has, of course, lots of collaborators. Professor Lau Diosi is a well-known figure in this field. Then experimentally. So the good thing about Thomas is that he works with hands in hand with experimentalists, particularly in optics. So he he collaborates with Professor Andrew Forbes in Johannesburg. And then Steph is of course a theoretician. And then he collaborates with Hans Briegel and also some of the Indians in India, like my former student Sandeep Goel, and sometimes with me also. So with this, I hand over to Thomas to start his colloquium.
Thank you very much, Subhashish, for this very nice and detailed introduction. Yes, I'm very proud to be invited here and to see you. It's wonderful to speak to you because this is such a prestigious institute, and I'm especially honored that now for the 60 years jubilee I was invited to give a talk. So I thought long about what I should talk about. So as you have heard, my expertise is actually in quantum mechanics and quantum information theory. But I have visited the IMSC from, I think the first time I was there, 2012. And right from the start, I got very much influenced by you. So I love the discussions in the tea room that you have. And in that tea room, I learned a lot about optics, I think, in discussions with Subhashish and Professor Simon. I don't know whether he is here, but yeah, so he taught me a lot, and they taught me a lot about the analogies of classical optics and quantum mechanics. And if you look at the first page here, then you see, can you see my mouse here? Is this visible? Can someone give me feedback? Do you see the mouse pointer?
We can see that. Yeah.
Okay, that's wonderful. So what you see here is a Rubrics Cube. And maybe you've seen it before, but on this Rubrics Cube, there are formulas from quantum mechanics and formulas from optics, classical optics, that is. And here you see, for example, the commutator of position and momentum is equal to, and here is a field with I times H bar. And of course, yeah, we know that formula, but if you know the Rubrics Cube, then you also understand that this part of the cube, namely this cornerstone, you will never be able to put it here, so that these three fields here are in line. And what you can do is you can actually bring this I here up, and then I claim you get a formula from optics that describes optics and not quantum mechanics. So let's see whether we'll find that again. And here is a few pictures of what where I see possibilities to actually use methods from optics in quantum mechanics, for example, for quantum information tasks, or the other way around, optics, quantum mechanics methods to characterize or do tasks carry out tasks in optics. So these fields really are very much related, and maybe more than one would think if one just has the usual textbook opinion. And I became so interested in this that I put effort into it to explore more and more what the analogies are. And here is an article that I wrote with Andrew Forbes together. He is an experimentalist, and it appeared in Contemporary Physics. So these examples are from there. And the first example here is on this side, is like a telescope with some plate here that only that does something to the light. So in the middle of the plate there is a hole, but otherwise it's a phase plate that changes the phase. And what it can do is it can actually transfer phases into amplitudes. So here you see an input distribution of certain modes. They can, of course, correspond to numbers. And if you want to calculate something with this device, then it could be that you search for something. You search maybe for this entry that is here, this number 42, which is here in yellow. And the reason why it is in yellow is that all the modes that come in have the same amplitude, but one of them has a different phase, a negative phase, while the others have positive phases. All right, and then you can map that onto a distribution where the one with the negative phase has a higher amplitude, and that means it sticks out and you can detect it. So in a sense, this is a machine that searches can search a database and can make one of the amplitudes more prominent so that it is more likely to be detected. This can work with single photons, but it can also work really with classical light. And the way it is done here is like there is some Gaussian profile that comes in, and there is really just a certain phase shift imprinted onto a particular part of the field. And then once it runs through here, you find a field. Here the field was like the amplitudes were it was like a plane wave, a little bit like a plane wave. It was a Gaussian, but let's say flat top. And then in the end, you find amplitude that corresponds to this field. It's on the opposite side, but it's the same. Okay, so this is one of the things that we can do, and later you will find that this is actually an application of Grover's algorithm, Grover's search algorithm, that can be used in optics, and I will talk more about that later. So here you see so-called vector beams where you have an electric field, electromagnetic field, and the electric field vector is varying over the transversal plane of the beam. So for example, here it's radially sticking outwards, and here it has a different pattern, but it's varying. And these beams are called vector beams. And as I will argue later, they show some kind of entanglement, which by Professor Simon was called non-quantum entanglement. And he used this to actually show that not all Müller matrices that describe the transformation of the polarization in some optical setup can be realized in the lab, but only those that correspond to completely positive maps. And this is a technique that he took from quantum mechanics, where non-complete or where completely positive maps are the physical maps, and this is well known that non-completely positive maps are non-physical. Okay, so you can use methods from quantum mechanics and apply them to optics. And here is another thing that I learned also from one of Professor Simon's papers, namely, it's the Wigner function of a spatial mode. I think it's a Laguerre-Gauss mode, and the Wigner function here has positive and negative values. And usually, if you know about Wigner functions, they occur prominently in quantum mechanics to describe the state of systems. And those Wigner functions that have negative values, they correspond to real quantum mechanical states, while those that are positive can be associated with probability distributions and are associated with classical states. So to find non-classical states in optics, and we are talking here about classical optics, not quantum optics, is of course for someone who is fresh, and I was fresh when I came in the field of optics, quite a surprise. Okay, so you can see there is a lot of analogies, and there is a cross-fertilization between the fields. And I want to ask today 3 questions. Namely, what can we learn from formulating optics in the language of quantum mechanics? Then is it possible to implement quantum algorithms by means of classical optics? And can classical light and nonlinear optics simulate non-local entanglement? So these questions are...
Hello, Thomas.
Yes, can you hear me?
We can hear, but your screen has gone off. So just...
Oh, so you can't see my screen?
No, from your side, it is okay. I think it is from our side, it's a problem.
You can't see my... Okay, then I just share again, I would say. Can you see my picture?
No, you don't have to share. It's fine. Let's see. I think there is some problem from our side.
Oh, from your side. Okay. Let me share again and see whether this makes a difference. Can you see this?
We can see in our laptop. Body to so I think there is some problem in the... So just wait for some time. Huh? Sorry for this.
Yeah, sure. No worries.
Yeah, now it has come. The state space of optics.
Oh,
yeah.
Wonderful. Yeah, okay, super. So thank you very much for your patience. And yeah, let me try to describe for you the state space of optics. Yeah, I see someone raised his hand. Is there a question? Ranjit?
No, sorry, no question.
No question. Okay. Yeah, feel free if you want to ask something. So here's the wave equation for the electric field of electromagnetic wave, which can be derived from Maxwell's equations. And you know, if we make an ansatz where we distinguish different variables, so here the spatial variables and time, and I also put here the direction of the electromagnetic field, then we can derive this equation here. And we see, you know, now we have a separation of variables, so that the left-hand side and the right-hand side depend on different variables, so they must be equal to a constant. And then we can write down 2 equations. In fact, we can write down 3 equations, but the 2 equations that come from the separation ansatz are here the first 2 equations. And the third equation is an equation that comes from Gauss' law. Divergence of the electric field in vacuum is 0. And that gives us this relation between G and epsilon. And then we should also note that the first 2 equations are coupled because we used here different you know, we have to look at the same constant here, which is minus k squared. And then if you multiply the c squared to the other side, you get a c squared times k squared, and I call this omega squared. Okay, then I get this equation. And yeah, this is well known, of course. But what I want to point out to you is that the general solution of the wave equation for the electric field is then, of course, given by superposition of products of basis solutions for the single equations. Okay, and this is already kind of pointing out that in general, the electric field cannot be written as a product of the different components. I mean, as the product of the spatial part and the temporal part and the polarization, but it is a superposition of this. And this is a kind of analogy to what we see in quantum mechanics when we have entangled states, all right? So non-separable states are those states that cannot be written as a product of different degrees of freedom, or of the states of different degrees of freedom. And I want to work that a little bit more out, and I want to argue that the total state space is now given as can be formulated as a tensor product of the solutions of the three different equations. And the tensor product, of course, we know these are linear equations, so it will be vector space, that's clear. All these components will be vector spaces, but I want to actually show you that they are in fact Hilbert spaces. Okay, and for that I go back to the Helmholtz equation, where now I have written it in terms of I've separated one of the variables, and then on the other side I have then just the variables x and y, and the Laplace in terms of these variables. Those are the variables on a hyperplane if I separate the z direction. And then you can see that in principle I can calculate, if I know the distribution of the values of G on some hyperplane at z equal to z0, I can, in principle, by solving this equation, find it on any other plane. In other words, I can propagate the spatial part of the solution in one direction, and that means the state is actually given just by some boundary distribution, and this is on a two-dimensional plane, on a hyperplane. Okay, and of course I can write down formally the solution by means of a propagator, which looks like this. You can check this by just taking the second derivative with respect to z, and then I want to point out that I use here the electric field as the complex valued electric field, and then also this G is now a complex valued function, and the Z is for me now a parameter. If I want to describe the state of the field, it's at least in terms of the spatial components, it's enough to have the X and Y. Okay, and then Z is like a parameter. All right. So from this, I would like to argue that if you look at this function gz of X and Y, then it will always be square integrable. And the reason for that is that it is related to the power of the electric field that is kind of transported through this plane. And the power is, of course, always finite, and therefore this integral here must exist if you really have a physical electric field. And then we can say, okay, this is a square integrable function. So in other words, the Hilbert space is a L2 element, where L2 is the Lebesgue integrable functions, square integrable functions from a plane to the complex numbers. And similarly, we can argue that also the time-dependent part is Hilbert space, and the polarization part is also Hilbert space. In this case, you can describe everything in terms of Jones vectors, which I have complex entries, and then you get C2 as a vector space. And so in other words, we have now a kind of a structure like in quantum mechanics. In quantum mechanics, it's like this, that if you have different systems, for example, you take an atom and a second atom, let's say, or I can also go within one atom. I take the, let's say, the spatial part and the polarization and the spin of the electron. So the distribution, the wave function of the electron lives in one Hilbert space, and the spin in a different Hilbert space, and the total Hilbert space of the electron is then given by a tensor product. Okay, and here in optics, I argue this is the same thing. We have a tensor product structure, and this has to do with the different degrees of freedom. So we can see the polarization as a degree of freedom of the electromagnetic light, electromagnetic field, and then we have the spatial temporal degrees of freedom, and they belong to different Hilbert spaces. In order to actually say that these are different degrees of freedom, they must be really, we must be able to choose them independently, and that is a little bit of we have to look at this closer, because you could think we know that there is a relation between this constant omega that appeared in the temporal part and the spatial frequency k. C was the speed of light, by the way, in the spatial part, and since this is fixed, let's say we have a fixed omega, or in other words, we have a fixed wavelength, then yeah, one would say, okay, it probably means that also somehow these things are not, we can choose them independently. For example, one could say, okay, if you have k squared, positive number, then this k squared, which is kx squared plus ky squared plus kz squared, is always greater or equal to kx squared plus ky squared, and that limits your choice of kx and ky. Okay, but I want to point out that it can also be the other way around. Only then you have the electromagnetic field that is decaying like this with the distance, and this is well known. This exists. These are evanescent electromagnetic fields, but it doesn't mean that so they exist. So this is also a possible solution, and therefore I want to argue these things are independently. You can choose them independently, and the same is with the polarization. The polarization can vary independently in the tangential plane. In each point, you have maybe a different tangential plane, but in this plane, you can choose the direction. Okay, so this is this, and it leads to this. Oh, now I've made. I want to go back. Give me a second because I can't see my own picture. I hope I get back. No, I don't get back. What you can I do it? Let me do it again. I'm sorry. I pressed the wrong button, and now I have to pay the price. And let's hope. There's my picture, and this picture shows these vector modes where exactly this happens. That we don't have polarization that is constant over the plane, and therefore, you know, we don't have a separable state in the sense of that you can write the electric field as a product of the spatial mode of some function on some hyperplane times polarization vector. No, you have to put in each polarization vector extra in each point of the plane an extra polarization vector. And here you see such a picture where if you have such a vector beam and you send it through analyzer with horizontal polarization, then you get these two distributions that have electric fields in opposite direction. And if you want to see this as a kind of entanglement, like entanglement in quantum mechanics, then I can tell you this is a very nice. There is a very nice way to characterize it, namely in terms of the measures for entanglement in quantum mechanics, and this has really applications because you can imagine that if you want to cut through a piece of metal with a laser, then you can use these kind of vector beams, maybe send them through an analyzer, and then you see that here is some tension between the even without the analyzer, there would be some tension between points where the electric field is kind of moving charges in different directions, and it might help your cutting process to use these vector beams. Okay, I want to say that we can use the Dirac formalism like in quantum mechanics, because now we established that like in quantum mechanics, we have these Hilbert spaces. And the Dirac formalism is a very nice way of, a very practical way of writing the states coordinate free and being able to look at it on a higher level and then go to only to the different representations like the momentum representation or the position representation when necessary. Okay, so this is it. And I don't know, I think you are probably very familiar with the Dirac formalism. I just go shortly through it. So, we have these bras and cats that if you put them together, they are brackets, they give brackets, that's an inner product. And you can write operators in terms of these bras and cats. So you write a cat behind a bra, this is called a bra, this is a cat. And the bra is like a linear form that acts on a vector and gives you a number. So using this inner product. And then you can put this number in front. And that gives you a very nice way of changing the basis. Namely, if you have some basis representation of some vector u, so these cats just correspond to vectors in your Hilbert space, and let's say there's a basis I, and now you have the coefficients alpha I with respect to this basis I, then you can write, of course, the alpha I, if it's an orthonormal basis, that's given by the inner product of the basis vector I with the vector u that you want to represent. And I can now group this differently. So I group the cat here that was standing behind. I write it in front. It doesn't matter where I put the number. And then I group the bra of the basis vector together with the cat of the basis vector. And I get a projector like I had it here with the W. And I can also, because the whole thing here is a sum, I can sum first all the projectors. And if I look at this equation, then I see, since this is holding for all vectors u, this operator here that I got must be the identity operator. Okay, so this is, I can write identity operator in terms of all kind of bases, and then I can write easily the basis representation of operators using this kind of sandwich product here. And we know that spectral decomposition of an operator is then also given in terms of projectors onto the eigenstates multiplied with the corresponding eigenvalues. Okay, so it's a nice formalism, and you wouldn't believe it. In optics, it's used. Maybe you are all in optics. I don't know. Then you know this, but it is so practical that even in classical optics, if you look in modern papers, they use the Dirac formalism. So I want to just go on a little bit more, but not too long, to show you why this is so nice to use the quantum mechanical formalism for optics, for classical optics. Namely, here I have such a state of the electromagnetic field, and here I have some observable. that could be the energy or the wavelength or the orbital angular momentum or the momentum or whatever of the electromagnetic wave. And we can write it because of the analogy to quantum mechanics in terms of, or we can represent it by an operator, self-adjoint operator. And then we can calculate the expectation value. And the expectation value is related to what you measure. So if you measure, if you have some distribution of wavelengths, for example, and each, so the wavelength now corresponds to a certain frequency of light, or so to a certain color also, if you want. And now you can, of course, kind of split it, decompose a general polychromatic wave into the single wavelengths, and then you can tell me what is the intensity with which each wavelengths come, and I can calculate the average wavelengths if I want, or average energy or so. And this is nicely given here in terms of the spectral value and of the observable. This can be anything, and basically the intensity that the electromagnetic wave has with respect to this. So as examples where this really plays a role, where one measures things in terms of this is, for example, here you can have these Laguerre-Gauss modes. This is modes that carry a certain orbital angular momentum, and these modes can be measured by using holograms that unwind the mode. So the mode is a little bit like, you can think of a corkscrew wavefront, and you can make it flat again by using the right hologram, and then you map this point here or this plane here onto a focal point here, and you make a pinhole in the focal point of this lens, and then all the light that comes through is basically the image of a plane wave here. So if you unwind this corkscrew into a plane wave, or even if you just produced a certain component out of this, then you can measure the intensity of that, and that would correspond to this eigenvalue. In this case, the eigenvalue L equal to 2, because the hologram only unwinds L orbital angular momentum value L equal to 2, and not the others, and then you can measure the intensity of this component. Okay, so you can decompose your electromagnetic waves into the components with respect to your eigenstates of the observable, if you want. And a more practical way, maybe this is not the most practical way, but this is a way to actually split it. So you always need mode sorters that sort the modes. In this case here, we have a sorting according to L values that are even and L values that are odd, and then L values that are divided by 4, and those that are even but not divided by 4, and so forth. And then we can sort the different L values in the end in a logarithmic number of steps, and then we can measure the intensities. All right. So this is how one measures things here. And a more practical way is that one really maps the. This is also a mode sorter, MS, but it's the so-called Paget gadget after Miles Paget, who invented it, or whose group invented it. And it allows you to unwind all these modes at the same time, all orbital angular momentum modes, but now they are mapped onto different, they get different transversal momenta. And then they are mapped on a screen on 2 different points. And then you can say, okay, in this point, I got this intensity. That means I had the L equal to 2 component at this intensity, and so forth. Okay, so this the basic thing. And yeah, I want to maybe go a little bit faster. You know, we can now write down the different states of the different degrees of freedom. And here I wrote the temporal degrees of freedom in terms of different. So I use this identity operator that resolves according to different frequencies. And if you have then such a state of the temporal part of the electromagnetic field, then yeah, you can get back the function f of t by going into the representation with respect to different times. So this is possible. This is a little bit like in position and momentum representations for wave functions, but yeah, so we can write it like this, and then we can do pulse shaping by using operators that put, depending on a certain frequency, a certain amplitude and a certain phase. And in classical optics, you can have amplitudes that are bigger than 1, so you can increase you can increase the intensity of the component that has omega, and you can give phase shifts, of course. In quantum mechanics, you cannot increase this. This is not possible, and then you have an operator that has a spectral decomposition like this, and there is a way to experimentally do this by having some grating that that separates the different wavelengths or the different omegas, and then you can put some, for example, some phase shifts on the different paths, on the different positions here, and then you get an effect like this. Okay, so we can do the same thing with position and momenta, or position and wave numbers on wave vectors. So here, if I use these cats xy, then by this I mean a point source. Okay, a point source that is only located in the transversal. Let's say we are, let's make it simpler. Let's say we have paraxial light, we have light beam, and then in the transversal plane at some point xy, I would have a point source, and I can now decompose everything in terms of point sources. So if I have some state vector, I multiply it with this identity, then I get the amplitude and phase in a certain point xy. The z is just seen here as a parameter, and times the state of the point source, basically. So it says this particular point source at x and y has a certain amplitude and certain phase, and I can decompose everything, every electromagnetic field that on the transversal plane by just adding these different point sources. Okay, so this is the idea, and the same thing we can do also in the momentum representation, and then we see that the momentum representation is related to the position representation by a Fourier transform. And why is that? Because the position representation of such eigenvector of the momentum representation of the momentum operator, if you want, is a plane wave. So if you have a fixed a transversal momentum, then you have here a plane wave. This is given like this, and this factor comes in again here, and then if in this integral you find that the position representation of your spatial mode is now related to the momentum, to its momentum representation by Fourier transform. Okay, and we can go further. We can define position and momentum operators, where I introduce here a scaling factor, which is the reduced wavelength lambda bar, so lambda over 2 pi, occurs often in this context. So it's good to actually divide it by 2 pi, and it's equal to 1 over k or c over omega. And then it is funny to see that in quantum mechanics we have the Broglie relation, which is p is equal to h bar k, but in optics we have here for the I put here a t because I'm actually talking about the transversal momentum. So how the electromagnetic field disperses, how the wave spreads in on a transversal plane. I'm not talking about so much about the propagation. I will do that later. And then you see that for the transversal momentum that was defined like this, it's related to the wave number, transversal wave vector. Sorry, with this lambda bar. And what might be even more interesting, or what is for sure more interesting, this is just a definition, is that you can now show that in optics, the position operator defined like this and the momentum operator do not commute, and that the constant that occurs, or the scale factor that occurs in the commutation relation, is now lambda bar. So this lambda, the wavelengths over 2 pi. And this is interesting because in quantum mechanics, there is only a single scale factor, namely Planck's constant divided by 2 pi, so h bar. And here in optics, there is many. In fact, you have here these Heisenberg algebras for all wavelengths. You have different Heisenberg algebras. I mean, with different, not different Heisenberg algebras, but with different constants in here. So one can argue that optics has more structure than quantum mechanics, and somehow this I feel this this reminds me of something that I heard from Professor Simon from your institute, who once said to me, if he would write a book on optics again, then quantum mechanics would be an appendix, maybe. So we see a lot of structure of quantum mechanics already in classical optics. Okay, so I would like to skip this in order to not use too much time. I can tell you that we can show that the Schrödinger equation for paraxial light, so under some approximation, namely that the main propagation direction is the z direction, looks very similar. So here's the paraxial wave equation in this formula, in this formalism, Dirac formalism, and here it is in the usual formalism. Looks very similar. Then similar as the Schrödinger. Okay, so both are very similar, and we see that the role of h bar is here played by a lambda bar. Okay, then one can use this to calculate things in optics. For example, we can derive the lens equation. Sorry. We can derive the lens equation using operator techniques. I don't want to go into it. And we can use the knowledge that we now have to characterize vector beams. I just want to shortly show this. So here is vector beams can always be written in terms of just a Schmidt basis. That means we have since we have only 2 basis vectors for the polarization, it's possible to also find 2 modes only that characterize any vector beam. And then we can write down things like the beam coherence matrix, which corresponds to the density matrix in a quantum mechanical setup, and something like an average polarization state that describes the average polarization, so averaged over the modes. And then we can write down the degree of polarization given like this, average degree of polarization. And this is related to to the concurrence. So in fact, I didn't write it down here. So the average degree of polarization I used here, a measure from quantum mechanics, is the entanglement of formation. But this is related to the concurrence, and one can prove now that the average degree of polarization is dual to the concurrence. So you can say if the average degree of polarization is P and the concurrence is this entanglement measure C, then P squared plus C squared is always equal to 1. Okay, and that means you can use either or to characterize the vectorness, or if you want, the entanglement that is present in these beams. Okay, and here is an idea what you can use this for. This would be, imagine that you have such electromagnetic field with all these different polarization vectors. All right, and you can now define a local degree of entanglement. Okay, so if you look at this blue part here, then you see that the vectors are more or less pointing in one direction. So I put it here on a Bloch sphere that can be used to represent the polarization, and there they look more or less, they point in the same direction. If I go to this blue square, but in the red square they point to all directions, so like this, and then the average polarization P is equal to 0, and here it's very high. So there's a high polarization here, while there is a small polarization here. And what we want to use this together, I work here together with Benjamin Paris, that you might also know. He also visited your institute. We would like to know how can we use classical fields to actually prepare qubits in atoms. So we use a classical field, and let's say there is a distribution of atoms in a gas, and now we polarize the atoms using the electric field, the electromagnetic field, and depending on what the polarization is, we have a certain freedom there. So if it's possible to produce a polarization of 0, that means we can produce vectors that point in opposite directions, and then we can produce qubits for on the quantum systems when the classical field couples to the quantum system. And this is now, if you think of such a plane which has a lot of pixels, let's say 1 million pixels, you would be able, by using the right polarization distribution, maybe if you have local polarization of 0 everywhere, to produce 1 million qubits in one go. So this is our interest in this, and I think I leave it here. I don't know how much time I still have, but to me it looks like 4 minutes. I'm not super sure. Can I have an indication of how much time is still left?
You can have about 9-10 minutes.
9-10 minutes. Is that without discussion or
without discussion? Without discussion.
Okay, super. Okay, then I just give you a fast run through this. I'm sorry that it took longer than I thought, but I already had the fear that this would happen. So what can we do? So the first question was, what can we learn from the analogy between optics and quantum mechanics? And one thing I learned is, well, it has a lot of structural similarities. We can use the Dirac formalism. We can use operators to describe observables in optics, and we can use the methods from quantum mechanics, operator methods, operator algebra, to solve optical problems. We can also use entanglement, possibly. And one other question could be, can we also actually use then optics to do quantum information tasks, for example, quantum information processing tasks. And then I'm here at this quantum computation with optics. And I can tell you that we have done this also. I think Sibašić was also involved in our discussions, and we've discussed this a lot. We found a few algorithms that can be transferred into or can be implemented with optics, but they cannot be implemented. There is a certain weakness in it, and I want to come to this in a moment. Maybe the first thing I want to convince you of is that Grover's search algorithm can be implemented using such a phase contrast microscope. So in some sense, this is an application of quantum information processing. What I would like to do, if you allow me, is maybe jump to the end of this. And if you have questions about the Grover algorithm and its application, I will come back later in the question session. Maybe one thing one can say about Grover is that it manages to increase the amplitude of a certain component. So let me just go back a little bit. I hope I can do it. Can I go back in this? Yeah, maybe then I don't go back. I just explain here what happens. So in this Grover algorithm, you start with a certain input field, and let's say it would be some Gaussian amplitude distribution like this, and then you run through certain steps. Here, the first step, I explain it now just in optics because maybe it's simpler. The first step is to imprint a phase at a certain point, and then a few other steps follow. An important step is this lens, which does a Fourier transform, and this is already kind of one of the big tricks in quantum computation. You always need a Fourier transform if you want to have an exponential speed. Or I don't want to say always, but if you have one, you can get exponential speed up. And then here is something called inversion about the mean, and this is done by putting a negative phase shift on everything except on the middle of the beam. And then there is a second lens, and if you look at the output, you get this this amplitude where the phase was given, or where the phase imprint was, where the phase was different. So this can be used to search a database and to actually increase or decrease the number of steps to find the database entry. Instead of, if you have a normal database, let's say of 100 entries, okay, then you would need, if it goes very bad, you need more or less 100 steps. Imagine your telephone book where you go through the entries and until you find a certain number and it's unordered, unstructured, then you have to of the order of 100 operations you have to do. While with this Grover search, you can do it in 10 steps, so in square root 100. And this is so because the amplitude is increased, and that means you can find this point that was marked easier. Okay, and in the classical waves, of course, it's really like it's just a matter of signal to noise ratio, and you can find it very easily. Okay, and this has been already kind of realized in the phase microscopy, and I just want to show you here a movie of, and I think then I will go on, a movie of a beam that is now transferred. So the amplitude of this Gaussian beam is transferred to the outside of the beam. Maybe I hope you can see here this point, so that in the end the beam itself becomes very faint. The intensity is very small, and all its intensity goes to one point. Okay, so we call this the Grover lamp, and you know, we have here a certain number of pixels, and we are able to transfer by just repeatedly putting you know, marking a certain point with a phase by transferring all the amplitudes in this one point. Okay, so this is what I wanted to show here in the simulation. I thank Benjamin for it. I hope one can see it. I realize that the quality is not too good. That all the light goes now into this one point that grows here, and this is one of the okay, this is maybe a fun application. It's not a real application of it, but we can do more serious things, and for example, encode database in terms of Gauss-Laguerre modes, Laguerre-Gauss modes, so with different orbital angular momentum. And then here we had, I don't know how many, 29 different modes, and we marked one of them, and then in an efficient process, we managed to measure this one point. And this was done with classical light. And now the problem is in this, that this axis cannot get arbitrarily big. Okay, so the point here is that even though we managed to efficiently implement all the steps in Grover's algorithm, we don't have enough space to store the data. You know, so if you look at the transversal plane, and you look at different modes that you can maybe these Laguerre-Gauss modes, and you find that given visible light, it depends on the wavelengths how much structure you can put into there, but given visible light, you can only get something like 20,000 or 22,000 OAM modes. And that restricts your state space severely, because in quantum mechanics, by having different atoms, I mean, let's say each atom is a qubit, you need maybe 200 atoms, and you have a state space that would correspond to 10 up to the 80 different points here. Okay, so this is a totally different ball game, and this is the crux. So while we think it's totally possible to do the things to implement in principle all quantum algorithms efficiently, we don't think that there is enough storage space, and this has to do with the fact that we have only these three tensor components that I've shown you. We can make it 4 if we see that there is an X and Y component, but so the entanglement is restricted to just 4 and not to more. And this means the multiplication of dimensions is not extendable. You know, we cannot go to 200 atoms, where if each atom has a Hilbert space of just dimension 2, we get 2 up to the 200, which is 10 up to the 80 approximately. So we can't do that. We don't get the large spaces, and this is the problem, in my opinion. And maybe I can tell you that we try to get out of this by looking at super oscillations. Super oscillations is a way to distinguish global frequencies, like in Fourier transform that you get from Fourier transform, from local variations. So even if you have a finite bandwidth in terms of frequencies, you can still have arbitrarily high local frequencies. You can generate arbitrarily high local variations, smallest periods, but it costs you energy, and it is very very difficult. You don't get, if you just look at the natural distribution of high frequencies, to get 10 orders, 10 times more frequencies than in your bandwidth. You have you find 0.1, or your probability, if you grab one mode out of all modes, your probability is 1/10, and to get 100 is already less than 1/10,000. Huh? Do I see this correctly? No, 1/1000. So this decreases exponentially. The number of modes that do this decreases exponentially, and we cannot really do it. We are afraid that we don't find a solution. We haven't looked. There is also the idea of super resolution. I haven't really looked into it, but it seems to also be difficult, and they also can just improve things by one order of magnitude. So to store things could be done in two ways. Either you store it, you use these extra oscillations, or you find you increase your resolution to store more, and this corresponds to the super resolution. But I think this can also not be done. So with this, I might want to stop here and maybe come to the conclusion. Sorry, I went one too much. This is not good. This is a different subject. I'm sorry. Yeah, now I have this problem of getting back, but I can do it. So here's the summary. So what did we see? We saw that that there is algebra of commutators that is non-trivial, and the wavelengths plays a role. Then there was the question, what can we do with the operator formalism to solve problems in optics? We talked about entanglement and how it might be used to do things in quantum information processing. And I showed you that, or I argued that that quantum computing might be possible with classical states of light, but the storage capacity is severely limited. And what I didn't show you is how to simulate non-local entanglement. It's possible, but I have to shift it to another day. Okay, thank you very much for your attention.
Thank you, Thomas, for such a wonderful talk. Question?
Thank you. It was a wonderful talk. Essentially, when we talk about some analogies between a way of seeing quantum mechanical structure in classical optics, obvious questions would be, there are various interesting or strange corners of quantum mechanics. How do they transform, or how do their analogs in classical optics side look like? So a couple of such things probably you didn't mention. One is the possibility of weak measurements. It would be curious, how do weak measurements or weak value measurements transform in classical optics setup like this? Another one is recent emergence of PT-symmetric quantum mechanics, which in fact the first implementation, they say, happened in this optical systems, in fact. So if you could speak a little bit about that. Thank you.
Yeah, that's very interesting questions. I must say I can't say anything concerning the second one. The weak measurements and the weak value is a big subject, and it is actually related to what I talked last about, namely the super oscillations. So it is possible to really understand the weak value in terms of local values of observables. So instead of looking at global values, we can look at local values. And I can point you to an article where this is discussed, where I actually discussed it. But I must say that I might not be able to recall it just out of my handcuff. But I can say as much as that this is possible. So that there is a deep relationship between the weak value and the super oscillations. And if you look at the articles of Barry, then you will find that Barry and Aronoff, they talk to each other, and this is exactly why they understand each other so well. Barry is very interested in super oscillations, and Aronoff is, of course, his school developed this weak value and the weak measurement. So unfortunately, I cannot really go into detail because I don't have it present. But I know that this is a big subject that can be exploited in classical optics as well. But for the second subject with PT symmetry, I don't know. Can maybe someone else wants to talk about this? I don't know. Yeah. But you are saying there is an optic. There was an optic realization or implementation.
Hello. So I had a question
yes.
regarding a talk.
Yes.
So in optics, we sometimes discuss. It's a very naive question, of course, that we discuss about Berry phases and Pancharatnam phases. So
yes.
in this operator formalism, how do you visualize those phases? And is it some kind of due to this entanglement that arises between different degrees of freedom?
Yeah, this okay, so again, I must say I'm not sure. So yeah, the Berry phase. I mean, there is this Aronoff-Bohm experiment in quantum mechanics, where you send, I think, charged particles, and you have some magnetic field that is confined in a solenoid, and there is absolutely no magnetic field measurable outside, but because of the vector potential, you can distinguish between different winding numbers as the electrons pass. I am not sure how you do that in optics, but probably this is somehow there. Can you give me a hint how the Berry phase plays a role in optics? I'm very sorry that I don't have that present.
I don't remember right now, but I heard once a talk by Michael Berry. He had this different kind of polarizers and analyzers which he uses in combinations to get a phase.
Okay, so he carries the polarization somehow around, I guess, and then gets a Berry phase. Yeah. No, I must say your questions are too good. I don't know the answer, but I will write it down, and next time I talk, I hopefully can give an answer. Okay, so Barry phase in classical Sutherland phase in classical optics. Okay, thank you very much. Sorry for this.
Okay. So here is one question in the chat box. Maybe I'll read for you. So
okay,
Pratik has asked a bit of name question, but is it possible to differentiate between the two categories, namely quantum and non-quantum of entanglement? Is it possible to characterize the strengths and limitations of these two types of entanglements with respect to computing capability, etc.?
Okay, yeah. So quantum and non-quantum entanglement. Yeah. So look, the non-quantum entanglement is a local kind of entanglement. So that is entanglement between different degrees of freedom of the same system. Okay. So you could also think of a quantum system like an electron. And then you can have, let's say, electron in the atom. You can have spin-orbit coupling, and you can have states that are entangled there. But it's the same electron, so you will never be able to show non-locality with this. So you cannot violate a non-local Bell measurement or something, a non-local Bell inequality. You cannot do this. And this is the typical case in classical optics, that you cannot do this. But you see it here in my last line, simulation of non-local entanglement. You can use non-linear optics to produce products of electric fields, and then this opens, even though you're not able to directly produce non-local entanglement, you can simulate it in the sense that if you have some nonlinear optical device, like a nonlinear crystal, and you send two beams into it, then there is some nonlinear process, so they interact. And in the end, you can measure something, and conditioned on measurement outcomes of the product field that goes out, you find certain correlations and non-local correlations, because the beams came from different locations, and these non-local correlations also violate Bell inequalities. And Subhashish and I have thought a lot about this, I would say. Subhashish, maybe later you can talk more about this, but this is a very interesting tool in order to check Bell inequalities and also in order to check local realistic theories and even just realistic theories. So hidden variable models. Sorry, and. So my point is, yes, this is one can look at the two things, and the non-local, so the strengths and limitations of these types, and the non-local entanglement is important if you really want to have quantum wires. For a quantum computer, you need to have different systems, or you have to be able to kind of interact. If you have only one system but different degrees of freedom, then each degree of freedom has to couple to each other degree of freedom. And the problem is that first of all, you don't, in a single system, you don't have so many degrees of freedom, or at least I don't know. I mean, it must be a very complex system to have many degrees of freedom, and then it also consists of different parts. And maybe if it's a classical system, then you would need a kind of correlation, a non-local correlation between these systems, and that classically you don't get. So there you hit a limit as well. So I think that only with the non-local, in other words, with the quantum entanglement, you can really do get this large storage spaces and so forth, and do things with it. Yeah, I hope this answers your question.
Hello. So you talked about this Grover search algorithm, right? So any
Yes.
kind of supremacy in quantum algorithm comes from the exotic quantum feature like entanglement or the quantum superposition. And you were saying using classical states of light, you can actually do this kind of you can reproduce this kind of exotic feature in your system. If you really can do that, I mean, like if you can really generate entanglement and the quantum superposition in your system using classical states of light, then can you really say that it's a classical states of light, or is it actually quantum? I mean, is it not a characterization that coherence and entanglement is not at all present in classical physics?
Yeah. Okay. So at the beginning, I thought you said something like quantum supremacy. So that refers to the ability to do calculations with quantum computers that you cannot do with classical computers in reasonable time. And this doesn't work as far as I know, and from what I think, with classical optics, because of the limited storage space. So this is not you couldn't do a supremacy experiment with classical optics. I don't think you can do that. Everything you do there is still simulable with quantum computers. Sorry, with classical computers. Therefore, it's not supremacy. So that's the one thing. Then the other thing, no, I don't think this is exactly the point. Thank you for that question. So you said, do we not, if we suddenly have entanglement, some form of entanglement in classical systems, do we then not have to say, oh, wait a moment, they are not classical anymore? Are they then quantum or so? And I think we have to distinguish there. As far as I know, you need a classical field theory in order to produce this non-classical entanglement. Sorry, this non-quantum entanglement, I want to say. So in order to produce some kind of entanglement, you need a classical field theory. I don't know whether you can do it with tennis balls. Let's say the spin of a tennis ball and its momentum. I don't think so, but I would be very interested if you can tell me that this is possible. So my point is, I want to convince you, or I want to argue that classical field theories have certain features that we thought are typically quantum features, and I think now, no. We confuse this a little bit. So we should relook at the typical quantum properties and ask, is this really something that we only see in quantum systems, or can we also see it in classical field theories? And if so, what is actually left? What cannot be seen in classical field theories? What is typically quantum? And I would say that this non-local entanglement, I mean, even though I say you can simulate it with nonlinear optics, but it's not really there. So that is, I would say, something that is typical quantum mechanical and characteristic for quantum mechanics. Do you have any other ideas? What could be not not at all visible in classical optics, for example?
Yeah, thanks.
Thank you.
Okay, so yeah, if there is no more question, it's already late. So let us thank Thomas again for this talk. Okay, thank you, Thomas. I'll contact you later. Huh? Thank you.
Okay, thank you very much. Thank you very much for your attention and all the best. Thank you. Thank you for giving me the opportunity.